In this video, we're going to talk about rational functions and their graphs. We're going to find the domains of rational functions, use arrow notation, identify vertical asymptotes as well as horizontal asymptotes, use transformations to graph rational functions, and graph rational functions. So first let's talk about domains of rational functions. Rational functions are quotients of polynomial functions. This means that rational functions can be expressed as f of x equal to p of x over q of x. P and q are polynomial functions and q of x cannot be equal to 0. The domain of a rational function is the set of all real numbers except the x values that make the denominator 0. Rational functions contain division. Because division by 0 is undefined, we must exclude from the from the domain of each function values of x that cause the polynomial function in the denominator to be 0. So in this first example, we're going to find the domain of f of x equal to x squared minus 25 over x minus 5. So what we do is we're going to set the denominator equal to 0 and solve for x. We get x is equal to 5. If we plug 5 back into the denominator, it makes the denominator 0. So x cannot be part of your domain. So x is such that x is all real numbers, but x cannot be equal to 5. Okay, so 5 must be excluded from the denominator. In this next one, we have g of x is equal to x over x squared minus 25. We're going to set the denominator equal to 0. In this part, we're going to have to factor. This factors into x plus 5, x minus 5. We're going to set each one of the factors equal to 0 and solve for x. So I get x is equal to negative 5 and x is equal to 5. So x is all real numbers, but x cannot be equal to negative 5 and x cannot be equal to 5. This next one we have h of x is equal to x plus 5 over x squared plus 25. Well, if you set x squared plus 25 equal to 0, whenever you take a negative value for x and square it, you get a positive value. So I'll write that out. If you take a negative value and square it, it becomes positive. So since that's the case, your denominator in this case would never be equal to 0. Denominator will never be 0. Because no matter what value you plug in for x, this is always going to turn out to be a positive number. It will never be 0. So in this case, x will be all real numbers. Next, we're going to talk about arrow notation. We use arrow notation to show the behavior of f of x as x approaches a particular value. So in this first one, we have x is approaching a. You got a plus sign up here. That means x approaches a from the right. Here you have x approaching a and you have this negative sign. That means x approaches a from the left. Then you have x approaching infinity, and then you have x approaching negative infinity. So we're going to use this graph. As you can see, we have vertical asymptotes here, and we have a horizontal asymptote. We have a vertical asymptote at x is equal to negative 3 as well as x is equal to 1. And then your horizontal asymptote is your x-axis, which is the same as y is equal to 0. So if you look at this first one, we have x is approaching negative 3 from the left. I'll write that out. X approaching negative 3 from the left. So if you look at the graph, let's we're coming in from the left. We're going to approach negative 3. When we get to negative 3, my graph goes down. Keeps going down, down, down. It's going down to negative infinity. This next one we have x approaching 1 from x approaching 1 from the left. So if we look at our graph, as we approach 1, this graph goes down, down, down. So this is approaching negative infinity. The next one says x approaching negative infinity. So negative infinity is out here and positive infinity is out here. So we want to come in from the right till we get to negative infinity. So if we come in from the right as we're approaching negative infinity, we hit this graph here. This graph is going to keep going and going and going, and eventually it's getting closer and closer to the x-axis. Okay, the x-axis is the same as y equal to 0. So it's approaching 0. So basically what you're looking for is to see what happens to x as you approach, what's happening to y as you approach x from a certain value. So in this case y is equal to 0 because we're approaching the x-axis. Okay. Gotta find my arrow. Oops, scroll back up. And the next one is, I guess that was it for that one. I thought I had 4 questions. I only have 3 for that one. Okay, let's look at the next one. This is a different graph. We have a horizontal asymptote at y is equal to 1, and we have vertical asymptotes at x is equal to negative 2 and x is equal to 1. So in this first one, we're going to approach 1 from the right. So we're going to come in from the right. We're approaching 1. As we get to 1, we hit this graph here. And as you can see, this graph is going up into positive infinity. Now we're going to approach 1 from the left. So now we're coming in from the left. As we get to the 1, we hit this graph down here. This graph is going down to negative infinity. The next one is x approaching negative 2 from the right. So we're going to go from the right until we hit negative 2. When we get to negative 2, we hit this graph right here. The graph is going down to negative infinity. Now we're going to approach negative 2 from the left. When we come in from the left, we hit negative 2. We hit this graph up here. It's going up to positive infinity. Now let's do x approaching infinity. So we want to go positive infinity. So we want to come out here. So we're going to approach it from the left. We're going to keep going, and we hit this graph here. This graph is hitting the horizontal asymptote. So it's going out to y is equal to 1. Okay, so your answer here is 1. When we approach negative infinity, we're going to do it from the right. Negative infinity is out here. As we approach, we get this graph, and this graph is going to keep going and going. It's getting closer and closer to the horizontal asymptote of 1. So this answer here is 1. Sorry, I got to put this 1 in here. There we go. All right. Now let's look at vertical asymptotes. Vertical asymptotes are vertical lines which correspond to the zeros of the denominator of a rational function. Anytime you have a variable in the denominator, it produces an asymptote. Can we have 0 in the denominator of a fraction? No. So if I set the denominator equal to 0 and solve, this will tell me the values that x cannot be. Those are your asymptotes. If f of x is equal to p of x over q of x as a rational function, in which p of x and q of x have no common factors, and a is a zero of q of x, the denominator, then x equal to a is a vertical asymptote of the graph of f. So let's look at this first example. We're going to find the vertical asymptotes. It says f of x is equal to x over x squared minus 1. So I'm going to set my denominator equal to 0, and I'm going to solve for x. I'm going to factor this. This factors into x plus 1, x minus 1 equal to 0. Set each one equal to 0 and solve for x. We get x is negative 1 and x is 1. Those are my asymptotes. So I've already drawn the graph here. And as you can see, we have a vertical asymptote, which is the dotted line at x is equal to negative 1. And we have the same at x is equal to 1. The next one is h of x is equal to x minus 1 over x squared plus 1. So once again, we have, if we set x squared plus 1 equal to 0, we will never have a value of x that will make the denominator 0. Okay, so denominator will never be 0. Okay, so in this case, there are no vertical asymptotes. So if this is the graph, as you can see, there are no vertical asymptotes. So now let's talk about vertical asymptotes and holes. If p of x and q of x have factors in common, it produces a hole in the graph. First, factor the numerator and the denominator and cancel out any common factors. The factor being canceled out produces the hole. The remaining factor produces an asymptote. So in this example, we have f of x is equal to x minus 5 over x squared minus 25. We're going to find the vertical asymptotes, if any, and the value of x corresponding to holes, if any, of the graph. So we're going to, first we can reduce this. X squared minus 25 factors into x plus 5, x minus 5. So whatever cancels out is the whole, and whatever you have left over produces the asymptote. So as you can see, the x minus 5's cancel out. I'm going to let that be equal to 0, and when we solve for x, that'll be our whole. When we cancel it out, we're left with 1 over x plus 5. X plus 5 is my asymptote when we set it equal to 0. So here I get x is equal to 5, and here I get x is equal to negative 5. So what does this mean? So x equal to 5 does not cause the denominator to be 0 when the rational function is reduced. So when we reduce this, we end up with 1 over x plus 5. If I plug 5 back in here for x, it does not make the denominator 0. However, it does make the denominator 0 in the original function. If I plug 5 back in here for the denominator, I get x squared, which is 5 squared, which is 25. 25 minus 25 is 0. So this makes x equal to 5 makes the denominator 0 in the original function. Okay, so I have a graph here, and this blue line here is your vertical asymptote. This is x is equal to negative 5. You're going to have a hole at x equal to 5. So if you go here, this is 5 here, is going to be a hole here on this graph. And the reason why we have to put a hole is because we cannot include 5 in there because it's going to make the denominator 0. Let's look at another one. We have f of x is equal to x plus 7 over x squared plus 4x minus 21. We can factor the denominator. We want to find two numbers that multiply to give me negative 21 and add to give me 4. We get x plus 7 and x minus 3. Whatever cancels out is the whole. Whatever we have left over is the asymptote. So x plus 7 cancels out. That's going to be my whole. When I cancel those out, I'm left with 1 over x minus 3. X minus 3 will be the asymptote. So I'm going to solve for x. I get x is equal to negative 7, and I get x is equal to 3 for my asymptote. So this is the graph. This blue line here you see is my vertical asymptote, which is x is equal to 3. We're going to have a hole at negative 7. So we're going to have a hole right in here. This is 7. Okay. All right, now let's talk about horizontal asymptotes. A horizontal asymptote is a horizontal line that tells you how the function will behave at the very edges of a graph. So we got this rational function. The degree of the numerator is n, and the degree of the denominator is the letter m. So that's basically the highest exponents that you see. So you have n here, m here, your highest exponents. If n is less than m, the x-axis or y equal to 0 is your horizontal asymptote. If n and m are equal, this will be your horizontal asymptote. Y is equal to an over bm. And if n is greater than m, the graph has no horizontal asymptotes. So let's look at this first one. We have 9x squared over 3x squared plus 1. Here n is 2 and m is 2. I'm just looking at the highest exponents in the numerator and the denominator. Since they are equal, my horizontal asymptote will be the 9 over the 3. 9 over 3 reduces to 3. So y equal to 3 is your horizontal asymptote. So this is the graph. As you can see, I have a horizontal asymptote, the dotted line, which is y is equal to 3. This next one, we have 9x over 3x squared plus 1. N is 1, m is 2. As you can see, n is less than m. 1 is less than 2. So in this case, the x-axis, which is the same as y equal to 0, is your horizontal asymptote. So you look at this graph, y equal to 0, once again, it's the same as the x-axis, is the dotted line, is your horizontal asymptote. The next one, we have 9x cubed over 3x squared plus 1. N is 3, m is 2. As you can see, 3 is greater than 2. And since n is greater than 2, or sorry, n is greater than m, there are no horizontal asymptotes. So this is the graph. As you can see, there are no horizontal asymptotes listed. Now we're going to use transformations to graph rational functions. We're going to start off with these base graphs. The first graph is f of x is equal to 1 over x, and the second graph is f of x equal to 1 over x squared. So this is a problem. When you graph, I'm doing this in parts, so I got shifts out here. So this first graph is the graph of f of x equal to 1 over x. That's this graph here. So we're going to start with this graph, and what I do is I use these 2 points to do my shifts. 1, 1. These are points on the graph. -1, -1. So we're going to use the number down here and the number here to do our shifts. So down here tells us whether or not we should shift left or right. And here tells us whether or not we shift up or down. Okay, so we have to go back to our horizontal and vertical shifts that we learned earlier in another chapter, another section rather. So if we have x plus 2, that means we're going to do a shift and I have it right here, we will shift 2 units to the left because we got plus 2 here. I know it's confusing because when you see a plus, you probably think you want to shift to the right. But when you're doing horizontal, a plus means shift to the left, a minus means shift to the right. So in this case, we're going to shift 2 units to the left. That means we're going to subtract 1 from each of the x coordinates. So these are my coordinates, the points that I just had on the graph. I want to subtract 2 from each of the x coordinates. So remember, your coordinates are x, y, x, y. So we want to subtract 2 from the x coordinates. This gives me -3, -1, and this gives me -1, 1. So those points, -1, the point -1, -1 has now shifted to the point -3, -1. And the point 1, 1 has now shifted to -1, 1. Okay? And since we shifted to the right, that means we're going to shift, since we shifted to the left 2 units, my vertical asymptote will now also shift 2 units. So now we have a vertical asymptote, which is here, which is x is equal to -2. When we started off, the y-axis was the horizontal asymptote. The horizontal asymptote is the x-axis, is what I meant to say. All right, so now we shifted those, but now we got to take into account the -1. So now we got -1. That means we need to shift down 1 unit. So we're going to shift down by subtracting 1 from each of the y coordinates. So now my coordinates are -3, -1, and -1, 1. We want to subtract 1 from each of the y coordinates. So it gives me -3, -2, and then -1, 0. Okay. So let's go ahead and put those points. Those points are already on the graph. We got this point here and this point here. And now your horizontal asymptote is now y equal to -2. Okay, because you have to shift the x-axis down 1. Y is equal to -1. Okay, so this is my final graph. All I did was do the shifts. Let's try another one. We got the graph of f of x is equal to 1 over x squared. We want to graph g of x is equal to 1 over x squared minus 6. So once again, I start off with 2 graphs on here. I know that -1, 1 is a point on the graph, as well as 1, 1. So we don't have any horizontal shifts, and the reason why is you don't have any numbers down here with the x squared. So you don't have to worry about horizontal shifts. But you do have a vertical shift because you have a -6. So we're going to subtract 6 from each of the y coordinates. So if we put in our first points, we're going to subtract 6 from both of these coordinates. So I get -1, -5, and I get 1, -5. And since the x-axis was my original horizontal asymptote, we have to shift that down 6. So now my horizontal asymptote is y is equal to 6. So this here is y is equal to -6. And we got these 2 points that have now shifted. So we got -1, -5, and 1, -5. So this graph is the final graph. So now let's talk about the strategy to graphing a rational function. And I don't expect you to graph these. I do expect you to do the Desmos calculator to help you get a sense of what the graph should look like. But these are the steps that you should follow. We're going to determine whether or not the graph is symmetric about the the y-axis or the origin. So we have f of negative x is equal to f of x. That's if they're equal, it's symmetric about the y. And f of negative x and negative f of x, if they're equal, is symmetric about the origin. You find the y-intercept by evaluating f of 0. You find the x-intercepts by taking the numerator p of x and setting it equal to 0. To find the vertical asymptotes, you set the denominator equal to 0. To figure out the horizontal asymptotes, you use the rules that we just talked about, those 3 rules involving the exponents. You plot at least one point between and beyond each x-intercept and vertical asymptote, and then use the information to figure out the graph. But like I said, I expect you to use the Desmos website to figure that out. So the first thing we're going to do is determine symmetry. So I want to calculate f of negative x, and I also want to calculate negative f of x. So let's calculate f of negative x. Whenever we see an x, I am going to plug in a negative x. So the function is f of x is equal to 3x minus 3 all over x minus 2. When I plug in negative x, I get negative 3x minus 3 all over negative x minus 2. Now let's calculate negative f of x. So that means change all of my signs in the function, in the original function. So now let's check to see if we have any symmetry. Let's see if f of x is equal to f of negative x. So we're going to look at this here. Is this equal to my original function? It is not. So it's not symmetric about the y-axis. Let's compare f of negative x to negative f of x. So we're going to look at this function here again, and we want to see if it's equal to this function here. As you can see, they are not. They're not equal. So it's not symmetric about the y-axis nor the origin. So it's no symmetry. The next thing we're going to do is we're going to figure out the y-intercept by calculating f of 0. So whenever I see an x, I am going to plug in 0. I end up with negative 3 over negative 2, which is 3 over 2. So my y-intercept is 3 over 2. To figure out the x-intercepts, we're going to set the numerator equal to 0. Solve for x. I get x is 1. So my x-intercept is 1. To figure out the vertical asymptotes, I am going to set the denominator equal to 0 and solve for x. I get x is 2. When you put this into My Math Lab, you have to write x is equal to 2. You can't just put 2. To figure out the horizontal asymptotes, we're going to look at the highest exponent in the numerator, which is 1, and the denominator is also 1. So since they are equal, my horizontal asymptote would be an over bm, which is 3 over 1, which is 3. So this is my horizontal asymptote. Now they want you to plot some points, and you just use your calculator to do this work for you. You're going to plug negative 1 back in for x in the function. When you solve, you should get 2. When you plug in 1/2 back in for x in the original function, you should get 1. When you plug 3/2 in for the function for x, you're going to end up with negative 3. When you do 5 over 2, you plug it back into the function, you get 9. And when you plug 3 back into the original function, you get 6. So I'm not going to go and write it all out. The one thing I do want to concentrate on will maybe be these fractions. So let's say we did x is equal to 3/2. You get 3 times 3 over 2 minus 3 all over 3 over 2 minus 2. So that seems quite messy, but if you get your calculator to do it, it'll work out. So you'll likely get like a fraction up here at the top. Um, let's see. We said it was -3, 9/2. So I get 3/2 here. And when I do the denominator, let's see. I get -1/2. So if you use your calculator to actually do the calculations for the fractions, you may end up with decimals, but don't forget to convert it back to a fraction, and that way you'll get your whole your numbers here. So I end up with -3 here. All right, so now I use the Desmos calculator and I got this graph, but Desmos calculator will not give you the asymptotes. It'll just give you the actual graph, but not these dotted lines. So we already said x equal to 2 is a vertical asymptote. As you can see, your graph never touches x is equal to 2. We also have a horizontal asymptote is y equal to 3. As you can see, your graph never touches y equal to 3. It gets really close to it. So if you can get the visual from the Desmos calculator and then you can put the asymptotes in there, you can get a feel of what the graph should look like. And then you can eliminate your options because this is a multiple choice question.